All right, so I'll go back to the title. So today's going to be about heat engines, and then we're going to run the engine backwards and get a refrigerator. And then we'll talk about the Carnot cycle much later, which is a very ideal specific pattern you can take an engine through. But today we're going to mostly talk about basic heat engines. Okay, so really quick, before we actually get into proper heat engines, we're going to go over the laws of thermodynamics. So I told you the first law, which was in equation form, sort of like a conservation of energy kind of deal. I didn't ever tell you the 0th law, because it's kind of stupid. The 0th law is like the transitive property. If you have one system in equilibrium with another system, and for our purposes that means they're at the same temperature. If you have A in equilibrium with B and B in equilibrium with C separately, then obviously A and C are in equilibrium with each other. Again, kind of a pointless law, kind of self-explanatory or even trivial, but it is a statement that your professors might whip out later. So I even mark it with a disparaging duh here. So 0th law, kind of trivial. First law we've already talked about. All right, so Paul and I agreed we were going to opt to not cover entropy in this class because treating it carefully kind of takes a while, and Paul is on a different schedule than me, so we're going to try and sync up. So just really, really quickly, I want to give you the idea of entropy because we'll use it in literally one step in this whole slideshow. So entropy, as you may have learned in chemistry, roughly speaking, corresponds to the disorder of a system. Now again, this is very roughly speaking. An example of a system that has low disorder would be if you have a container and a gas is trapped in, like, let's say the upper third of the container. This would be low disorder. Okay. And let's say that's like a plastic membrane or something holding the gas back, and I poke a hole in it, and the gas slowly disperses and spreads throughout the container. This would be high entropy. Again, roughly speaking, it's just the gas is more organized when I've squeezed it into a smaller volume. And if I allow it to freely expand, it'll expand out. Disorganized. Again, it's kind of weird to talk about organization as being something that you put a number to. And there are strict definitions of entropy that you can actually get really hard numbers for exactly how organized something is. In a lot of applications, you'll use like k-log number of microstates. You'll learn that in chemistry, but we're not going to talk about it. We're just going to stick to its disorder. Okay, the second law of thermodynamics is that during any process, no matter how perfect or imperfect it is, if there's friction or not, at best, S stays the same. Okay, so S will never go down. At best, it stays the same, and it can increase during a process. So it at best stays 0. Otherwise, it increases. Okay, it can never go down during a process. So as an example, if you take a box and you rupture the membrane with holding the gas back, the gas will spread out naturally. However, the reverse is never true, or at least it's exponentially small probability for a gas to reorganize itself all into the upper quadrant. As you take many molecules, it becomes probability 0. So you see this process. This process is allowed by the second law because entropy increases. And this process on the right, where you go from high to low entropy, is disallowed because entropy would be decreasing. Now again, there's lots of rabbit holes here with like, oh, what if it just perfectly, all the pool balls perfectly bounce into the exact way that gets them all into the upper corner? There's rabbit holes with that, but we're going to skip over them. Okay, why we care, 2 reasons. 1, if entropy change is 0, a process is reversible. It can be undone. So entropy change is 0, process is reversible. Meaning if you put the energy in the opposite order when we do an engine, you'll be able to undo the process, take the gas inside of the engine and undo what was done. And again, this is if the entropy stays 0. If the entropy increases, you can't go back. You can't decrease the entropy in a reverse process. Only in a reversible process where the entropy didn't change overall can you reverse things. And I guess I'll just say where entropy increases, this is actually pretty rare in our course. Actually, I'm going to say we won't see this at all. We will only deal with perfectly reversible processes. So we won't see this. We'll always be dealing with delta S equals 0. Sorry, this is a delta S, change in entropy. So as unintuitive as it sounds, we're going to be able to run all of our engines backwards by taking the energy that the engine gave you and stuffing it back in and forcing the engine to run in reverse. Okay, so we won't actually ever see entropy increasing, so everything will be reversible for us. Okay, and lastly, I'll write down an equivalent version of the second law, which is that heat never flows from cold objects to hot objects spontaneously. Keyword spontaneously. You can force it to do that if you input energy, but it's not going to do it by itself. So heat does not flow from cold to hot temperatures without outside help or without outside energy input. Again, this is an equivalent way of saying the second law. If you guys remember, I actually said the definition of temperature actually involves entropy. This is sort of why temperature is sort of intrinsically linked to entropy and the direction of heat flow. It's defined as a derivative of entropy with respect to energy or something. 1 over that. But we won't use that. So as far as we care, we're only concerned that heat will never flow spontaneously. But with outside energy input, we can make heat flow from a cold object to a hot one to cool down the hot object, or the cold object. Okay, everyone good on this slide? Again, this is just a survey of the laws of Thermo. All right, now we're actually going to start talking about engines. We'll use that later when we get to the Carnot cycle. Okay, so first we're going to talk about reservoirs, which are very, very large objects. Normally when you take heat from an object, its temperature decreases according to MC delta T. But if you make the object extremely large, its temperature basically stays the same. Okay, so they're very large objects, and if you take some heat from them, the temperature doesn't change. Just because they're so big, temperature basically doesn't change. Now, the idea of an engine is going to be we want to take heat from something hot and you convert that heat into like a push. So we want to make the engine do work by, let's say, making a gas expand. So we steal heat from a hot reservoir. So I'm going to draw this in red. Heat flows out of the hot reservoir, and we're going to try and make that heat into work. We're going to try and make something expand to, maybe make a car move or something like that, twirl a piston. Okay. Now, you might be wondering, why do you need two reservoirs? I see here engines need two reservoirs. Why can't I just take heat straight from the hot reservoir, put it into the gas, and have it expand? That would do work. So it would, but the issue is then the gas is not in its initial state. Like, in order for an engine to work, you need the gas to come back to its initial state so it can do the compression again the next time the cylinders in your car compress. So the gas needs to return to the initial state. And that's what we're going to use the cold reservoir for. And again, this is just so like you can run the process over and over and over and over and over. So you can repeat the process. I'll fill in the other blank in a second. Okay, so we have a hot reservoir. We're going to use that heat to maybe expand the gas, and the gas is going to do work. I'm going to subscript it work out. We've always been dealing with work in. I'm going to do work out, and I'll talk about that in a second. Okay. Let's say the gas has expanded due to that heat. Now, after it has done the work, we need to cool the gas back down and bring it back to its initial volume so it's ready to go again. And that is going to require the gas giving off some of the excess heat it has obtained to a cold reservoir. And you need the cold reservoir because the gas needs to give heat off to something else. Right? It needs to be a lower temperature than the hot reservoir. The gas takes heat from the hotter thing, right? The heat flows from the hot object into the gas. The gas does its work, and then the gas is reset back to its initial position by some processes where it expels excess heat to the cold reservoir. Okay, so we have this diagram of the energy/heat flow in an engine over the course of a cycle. Okay, Q hot is the amount of heat coming out of the reservoir. Q cold is the magnitude, it's a positive number, the amount of heat going into the cold reservoir. And work out is the amount of work that the engine does on the car or whatever the engine is powering. So Q hot and Q cold are positive numbers representing the magnitude of heat flow either into or out of the reservoir, out of the hot reservoir into the cold reservoir. I'm going to use RES for reservoir. So magnitude of heat flow out of the hot reservoir or heat flow, I'm going to call this exhaust, by the way, exhaust heat, into the cold reservoir. Again, they're both positive numbers. Q cold being 100 means 100 goes into the cold reservoir. Q hot being 500 means 500 was taken out of the hot reservoir. Okay, so I was going to do this on the next slide, but I think it's probably more appropriate here based on how I explained it this time around. So we're going to write the corresponding conservation of energy equation from this diagram. It's pretty easy to read off. Q hot comes in and it splits up Some of it becomes outputted work, and the rest of it becomes the exhaust heat. So our equation is over a whole cycle, Q hot equals work out plus Q cold. Right? Basically, if you take 500 for Q hot, maybe the engine does 100 joules of work, and the other 400 joules of heat left over are expelled into the cold reservoir. Okay. You can view this as simple conservation of energy, and that's the way I like to view it, right? The engine doesn't have heat building up in it, right? The gas doesn't keep getting hotter and hotter and hotter each cycle of the engine until it explodes. It always comes back to the same temperature. So any heat that goes in must eventually leave when you repeat the cycle. And again, I'm just going to write that in parentheses. It's basically just conservation of energy. Since the gas must return to its initial temp. Since gas returns to initial. And I would really encourage you just to draw these diagrams. We're going to draw them for every problem. Now, I just want to remark something. The book says that this is the first law, which is technically true, right? When the temperature comes back to initial, delta E thermal equals 0. So it's sort of like net Q in equals net work out from the first law, but we sort of understand it better than that. You'll also see this written as work out is Q hot minus Q cold. Obviously, it's the same equation. And just a remark here, this is outputted work. We've always been talking about positive work being like injections into the gas, making the gas more energetic because you squeezed it and it has more energy now. Here, if workout is positive 100, it means the gas has given off 100 joules of energy to the surroundings. Okay, it's related by a minus sign to work in. The reason for this ugly introduction of another minus sign that can snipe you on a test is because for engines, the quantity you care about is how much work output there is, right? You care about how much energy it gives to the car. You don't care about how much energy the gas has intaken from the car moving. It doesn't make sense. So to avoid those minus signs, we are going to talk about work out. This will also help you use equations from the textbook because they all use work out. Yes? When QH equals QC, that just means no work is being done, outputted. Basically, heat is going into the gas, and all of it's leaving. No energy would be, no useful work would be done in that case. Yeah. Okay, I believe the book uses WS, work system, for this variable. So I just want to caution you, if you choose to read the textbook, they may use work system as the outputted work. Okay, so again, I'm skipping this slide. I wrote all the information on the previous slide. Okay, so just as a quick check of our understanding, let's figure out how much work is performed by each engine. Again, it may seem like child's play, but it's because the diagrams are drawn. If when you're doing problems you choose not to draw diagrams, you run the risk of turning child's play problems into really, really hard infinite loops. So as you can see from the diagram, if you choose to do it in equation form, you would have Q hot equals work plus Q cold. Sorry, work out plus Q cold. In this first example, Q hot is 100 coming out of the hot reservoir. Work out, we don't know. Q cold, remember, we always define it as the magnitude of heat flow, so it's positive 60 joules. So that tells us that work out is 40 joules for this problem, or for system A. Okay, again, that sort of makes sense intuitively. If you have 100 coming in and 60 is leaving, what's happening to the other 40? Well, it's being used as actual useful work. You could do this problem in reverse if I covered up to 60, and I told you an engine takes 100 joules from the hot reservoir, does 40 joules of work, how much does it blow off to the cold reservoir? You could do this problem just the same, right? The other 60 goes into the cold reservoir. Second engine, again, it's taking out 200 from the hot, blowing off 160 in exhaust, and the other 40 are actually being used as useful work. Okay, and then the other two are pretty obvious, 30 and 50, just from looking at the diagrams. You don't need to copy all of these down. Really only the first one or two is necessary to understand. Again, but we're going to draw these diagrams. We're going to stick to our plan of drawing the figure, because without it, you can get screwed. Okay, so we're going to talk about the efficiency of engines a lot. That's going to be the main question when I give you an engine. We're going to talk about the efficiency. And efficiency tells you how much useful work output there is, divided by how much energy you took from the hot reservoir to begin with. Okay, so the equation is going to be the efficiency is this symbol Greek eta. It looks like a giant curly N with a very long tail. Let me draw it a little better. Okay, eta is work out over Q hot. Right, so in our diagram here, if we take 100 joules, let's say, out of a hot reservoir, and we do 60 joules of work with it, the efficiency would be 60 over 100, or 0.6. And again, this is called the efficiency, and it uses this Greek eta, which is the Greek letter that pronounces like E, but it looks like an N. Okay, now something I just want to remark here. This seems to not care about the amount of exhaust heat, right? It only cares about the work out and how much heat you took from the hot reservoir. Right, so it seems to completely ignore the exhaust heat, which I guess is sort of true. You just take the work out, divide it by the hot reservoir. But remember that work, the hot reservoir heat, and the cold reservoir heat are tied together by that equation. Q hot equals work plus Q cold. Right, so Q cold is actually, if I tell you work out and Q hot, you actually know Q cold, right? Even though I didn't have to draw it to answer the question, we knew Q cold was 40. Right? Q hot equals work out plus Q cold. So if I want to, I can plug in work out equals Q hot minus Q cold into the numerator of this equation to get an alternate form. Okay. I'm going to write it on the same line rather than on its own line, just so you recognize they're the exact same formula. Okay, Q hot divided by Q hot gives me a 1 minus Q cold over Q hot. Okay, again, this is the exact same formula. Hypothetically, you never even need to use the other one, because if you know Q cold and you know Q hot, you know work. Or if you know work and you know Q hot, you know Q cold. But it'll save you an algebra step if you want to use it. And again, if you draw the diagram, you'll see you actually have two ways. If you completely panic and forget that there's an alternate form, you'll be all good. So whenever you're told like how much hot reservoir heat is pulled and how much exhaust is given out, and you say, oh, I don't have work out, I can't find the efficiency, the alternate form is there to save you. Or you could have drawn the diagram, found the work that way, and then used the original form. So there's a lot of safety nets with efficiency. Any questions on this? Just a remark, efficiency can never be greater than 1. So eta must be below 1. I'll put less than or equal to for now. Later, we're going to find that it actually needs to be less than a number like 0.9 or something, depending on how hot the reservoirs are. So later, it'll be less than like 0.9 or something. So we're actually going to keep pushing it. Engines have to keep getting less and less and less efficient. Everybody good with copying down stuff on this slide? No? Oh, good. All right, so here's a quick example problem straight off the homework. It should only take about 2 minutes, so hop to this. And again, draw the diagram, and it'll turn a potentially hard problem into a piss easy problem. Again, sketch the diagram, and it should become pretty simple. Anybody need more time on this? All right. So we're told it does 200 joules of work per cycle, and it blows off 500 of exhaust. All right, you can use the equation Q hot is work plus Q cold, or you can just look at it and tell that that upper arrow must be 700 for Q hot. Okay, you can use any of the equations. You can work divided by Q hot is the easy one. If you wanted to, you could do 1 minus Q cold over Q hot. Either way, you get 200 divided by 700, so 2/7. And this is probably like 0.29 or something. I don't know if it's exactly 0.29. It might be like 0.28 or something. Okay, and just a remark, efficiency is unitless. It doesn't have units of like joules or anything. You can tell because it's like Q over Q, or like it's an energy divided by an energy, so it's unitless. It's just it's like a fraction. Any questions on this? Again, if you drew the diagram, should be pretty straightforward. All right, so here's where it starts to get real. And it doesn't escalate as quickly as you think it does, but it visually escalates very quickly. So here I have a diagram of a gas being brought through a couple processes, forming a heat engine. Okay, and I'm going to ask, what is the efficiency of the heat engine? Okay, so in order to know the efficiency of the heat engine, in order to know the efficiency, I need to know how much work output it has and how much heat flows into the gas over all of the steps of the process. Okay, so I need work output, and I need how much heat flowed into the gas during any of the legs. Now, just a note here, and this actually is going to be pretty important. Q hot, I need to keep track on each leg of the diagram if heat went in or out. Because any leg where heat goes in is pulling heat from the hot reservoir. And any leg where Q is going out is blowing off excess heat to the cold reservoir. Okay, so I need to keep track of each individual process and figure out if it's taking heat from the hot reservoir. That would be a Q hot flow, basically pulling heat from the reservoir into the engine. Okay, so only heat inflows. Okay, now one concept we're going to use a lot is that normally we have work in equals negative integral of PdV. Or I'm going to say minus the area under the curve in this PV graph. That was for work in. We've moved on to the negative of work in. We care about work out, which is just equal to the area under a curve. Okay, we don't have the extra minus sign. And we can check that this sort of makes sense. If a gas expands left to right, it does positive work on its surroundings, so there's a positive work output. Now, when you have a cycle like this going right and then back left, the area as you go to the right will be this whole red area. And then as you go back to the left, the work associated with that left horizontal line will be negative of this green area. So that double shaded region will cancel out. And the net work done over the entire cycle is just going to be the area within this blue triangle itself, right? It's the enclosed area. Again, the reason is that when you're going from left to right on that upper diagonal corner, you are doing a lot of work, but then as you go back to the left, that green shaded area contributes negative work out. So at the end of the day, the area inside of that closed triangle is the total work output. Okay, so we can actually finish this problem immediately. Let's see if we know work output and if we know how much heat flows in. So the work output is going to be the area in the triangle. So work is going to be 1/2 base height is the area of the triangle. So delta V, the base, is 0.1. The height of the triangle goes between 20,000 and 40,000, so the height is 20,000 pascals. I think I deleted my example solution for this. Does anyone have a calculator to get what this number is? 1,000. Is it 1,000? Okay, perfect. Wait, that's so, totally should have done that in my head. All right, so the work output from the area was 1,000 joules. And the diagram in this case tells you, right, in this case the diagram tells you 4,000 joules of heat flowed in along that upper leg. So Q hot is 4,000. Okay, and at this point you divide 1,000 by 4,000 to get eta equals 0.25. Okay, again, so we cared about the area inside of the cycle to get the work. And then in this problem we got lucky. The problem told us how much heat flowed in. The next slide I'm going to remove that crutch, and we're going to have to calculate the heat that flows in along each leg of the cycle. And that will be the most general, hardest possible heat engine problem. Okay, again, any questions on my approach to this problem? Yes?
We're going to have to use like E equals Q.
Yes, so his question was, are we going to, when I said in this problem you got lucky, I told you exactly how much heat goes in. When I don't tell you, you're going to have to use like the first law, like Q equals delta E minus work or whatever it is when you rearrange the first law. You're going to have to manually calculate Q in. Okay. First, I want you guys to practice on a similar example. Okay. In this case, I tell you the sizes of the heat exhausts from the system rather than the amount of heat in. So you're going to have to draw one of those diagrams and figure out the heat that goes in for use in the formula. You don't know Q hot. Okay, so take a crack at this problem. Again, draw that diagram just to keep yourself organized on Q hot, work, and Q cold. And then use that process of the area inside of the cycle is the work. And again, I actually have upgraded my game. I list which exact homework problem this corresponds to on the top of the examples. I don't know what I said here, expelled heat instead of a cold reservoir. I think it meant to say into the cold reservoir. There's a couple ways to do this problem once you've completed step 2, because you'll know Q hot, work, and Q cold. Remember, when Q is going out of the engine, it's being expelled into the cold reservoir. So those two totaled up is going to be the total heat going into the cold reservoir. Q2 is not the work done. Q2 is being expelled into the cold reservoir. Sorry, the diagram is just weird. All right, so I'm going to go over this. So first problem is compute the work done during a cycle. And the work done is just the area inside of that closed curve. Okay, so area of the rectangle, just multiply the two together, and you get the width is 100 e minus 6 meters cubed, and the height is 300,000 pascals. So you multiply them together and get work out is 30 joules. And again, that's just from taking the area. Okay, we're told the total amount of heat exhaust are 60 along one part and 80 along another part, so 140 joules total of exhaust heat. You can either just look at it or use the equation to get that that red arrow has to be 170 joules worth of heat from the hot reservoir. Okay, and then the efficiency would be work divided by hot, which is 0.176. Again, you could have done it using 1 minus Q cold over Q hot. You'd get the same answer. All right, next class, we're going to talk about when Q2 and Q1 are not told to you, and you have to calculate them. All right, I'll see you guys on Monday. Have a great weekend.